Hi, my name is Aaron Greenberg. I'm an undergraduate researcher at the University of Pittsburgh, working with Dr. Jeremy Levy's group, and I'm going to be speaking today on the conductance of lanthanum aluminate strontium titanate nanostructures for temperatures between the freezing and boiling points of water. Lanthanum aluminate strontium titanate is a really fascinating material. It exhibits such interesting properties as a high-mobility two-dimensional electron gas that forms here at the interface between the lanthanum aluminate and the strontium titanate. It also exhibits a metal insulator transition, superconductivity, magnetism, tunable spin-orbit coupling, and more. We know that the properties of this two-dimensional electron gas are strongly correlated to the thickness of the lanthanum aluminate, and for such thicknesses of the LaO as 3 to 4 unit cells, we find that the two-dimensional electron gas takes on a base insulating phase, but it can be locally transitioned to a conducting phase. We use this property to create devices in LaO-STO, such as electron waveguides, single electron transistors, nanocross devices, and more. We do this through a technique known as conductive atomic force lithography. By applying a positive voltage to an atomic force microscope tip and dragging this positively biased AFM tip across the surface of the sample, we locally transition the 2deg from its base insulating phase to the conducting phase. By applying a negative voltage to the AFM tip and dragging it across the sample, particularly over areas that we've already written with a positive voltage, we're able to erase the conducting channels, returning the 2deg to its insulating phase. This writing and erasure process is easily repeatable and does not damage or degrade the sample in any way, meaning that we are able to use one sample for many tests. This works through something known as the water cycle mechanism, where water in the air adsorbs onto the LaO surface where it dissociates into H+ and OH- ions. The positively biased tip removes those OH- ions, leaving just the H+ on the surface and producing the conducting interface that we need. The negatively biased tip removes those excess H+ ions, which restores the insulating state. However, due to the excess ions in the air, we find that as soon as we write a segment of wire, it begins to decay. And this decay occurs over a timescale of hours. However, given that our writing is typically done for speeds between 10 nanometers per second and 1 micron per second, this severely limits our ability to create large and complex devices. So we look for ways to slow this decay so that we're able to write more intricate devices and do longer timescale tests. We know, however, that by placing a sample into vacuum or dry gases such as nitrogen, we're able to strongly arrest the decay of one of these nanowires, and by placing the sample into a dry gas or vacuum and then cooling it down to, say, 80 Kelvin, we virtually stop the decay of these devices. So this begs the question, just how does temperature affect the decay of a nanostructure written in LaO-STO? And that's what I set out to test. We did this by first writing a device in an AFM, and then transferring the written sample to a cryostat, such as this quantum design PPMS. We then vary the temperature at regular intervals, all while monitoring the conductance, so that we're able to get the conductance as a function of both temperature and time. For our first experiment, we focused primarily on the cooling of samples, that is, for temperature ranges between 275 and 300 Kelvin. The tests were done in air, on a nanowire written for 4-terminal measurement, as you can see here in the bottom left. Red represents the insulating LaO-STO, whereas green is written areas, and gold is the electrodes. The air in the cryostat was held constant, that is, the chamber was sealed with the air and the sample inside it. We used 1-hour time intervals for each temperature, that is to say, we placed the sample in the cryostat at 300 Kelvin, and then we allowed it to decay for an hour, at which point we decreased the temperature by 5 Kelvin, seeing a characteristic jump in conductance, and then we allowed it to decay again. We repeated this for 295, 290, 285, 280, and 275 Kelvin, and then we applied a linear fit to each one of these temperature intervals, giving us an approximate value for a slope of this time. To analyze this data, we first began by taking the natural log of this rate of change and plotting against the inverse of temperature. This obeys something known as the Arrhenius equation, given here by dg dt, the rate of change of conductance, is equal to A, a rate constant, times e to the minus Ea, an activation energy, over kBt, where kB is Boltzmann's constant. Therefore, the slope of this line can be used to give us an activation energy for the decay function, and we find that to be approximately 0.77 eV. Now, Sanjay Adhikari in Cheng Sen's group at the University of West Virginia has done theoretical work on LaOSTO, and they find that they expect the surface proton hopping energy for LaOSTO to be similar to values obtained in water-only clusters, or about 0.7 eV. This shows that the theoretical work is agreeing with our experiment work. We then looked for another interpretation of this data, and we did this by plotting the average value of conductance for each time interval over the rate of change to give us an estimate for the time that one of these devices will remain intact. At 300 Kelvin, we see a lifespan of about a day using this estimate, which agrees with the experiments that we've done, where we simply write a device in air. But we see that for a temperature of 275 Kelvin, we find a lifespan of about 23 days, showing that a very modest cooling of these devices can lead to a very significant increase in their lifespan. We then wanted to look at both the cooling and the heating of these samples. So we focused primarily on the heating while still investigating the cooling. We again performed the test on a sample in air with the air sealed in the chamber, and we added a two-dimensional device to the schematic to see if there was any difference in the decay between the one-dimensional device, this nanowire, and the two-dimensional device, this box. There's no significant difference, so we're going to focus just on the one-dimensional data. For the air test, we held the time constant fixed at about an hour. Again, we began by keeping the temperature at 275 Kelvin this time, and then increased it in 1 hour intervals. And what we see is that for low temperatures, below 340 Kelvin, we see the sample behaving as we saw in the previous test, where an increase in temperature increases the rate of change of conductance. However, for high temperatures, we see a global background conductance effect begin to rise, and it very quickly dominates the sample's conductance, overpowering the device conductance. We don't know much about this background conductance effect. It's currently the area of more study, but it does seem to be entirely temperature dependent and is not dependent on the gas species that the sample is stored in. However, returning just to the lower temperature regime between 275 and 335 Kelvin, we are again able to take the natural log of the rate of change of each of these temperatures, plotted against the inverse of temperature in, again, the Arrhenius equation, and we get an activation energy for the decay of 0.67 eV, which again agrees with the theory. So in conclusion, we've shown that very modest cooling of devices can dramatically increase the device's lifespan. Extending our device's lifespan allows us to create more complex devices and larger devices, which allow us to study new interesting effects. We want to study LaOSTO's behavior at high temperature because if we understand how it works, it opens up the potential to do tests where we subject the sample to high temperatures, such as annealing samples in oxygen, or surface studies of the samples, or simply applying high voltage to the sample, which may cause arcing and therefore high temperatures on the surface. Understanding LaOSTO's behavior at high temperature lets us better understand the mechanisms behind the c-AFM lithography and gives us new insight into how the system behaves. I'd like to thank you for your attention, and if there's any questions, please direct them to either Jeremy Levy at levylab.org or myself, Aaron Greenberg, at levylab.org. Thank you again. Have a nice day.